Hello, I'd like to tell you about Markov chain robustness. Markov chains are used to model diverse phenomena. However, in many situations, we don't expect the chain to be followed exactly. For example, the chain may model nature or social interactions. Another example is if a continuous chain models some continuous phenomenon exactly, but when we discretize it, we introduce some noise. So it's natural to ask, how robust is a Markov chain to noise? This can be studied in the framework of Markov set chains. A Markov set chain is a collection P of n by n stochastic matrices. And the Markov set chain is a stochastic process xt on the states 1 through n. At time t, an adversary chooses pt from this class P, and the next step in the chain is chosen according to pt. Similar models have been studied by Azar, Broder, Carlin, Lineal, and Phillips, and more recently under the terms like dynamic graphs and evolving graphs. However, our perspective will be quite different than these previous works, and I'll discuss that towards the end of the talk. Our focus will be on random walks on undirected graphs. Now let's talk about the power of the adversary. So there are three natural choices. One is that the choice of PT can be independent of XS itself, independent of the whole process. In other words, decided in advance. The second choice is a Markovian adversary, where PT can depend on XT, but otherwise it's independent of previous XS for S less than T. And the strongest adversary is the non-Markovian adversary, where PT may depend on XS for all S less than or equal to T. Now suppose pi is the stationary distribution for all PT. And let's assume all the PT are ergodic. In other words, they correspond to random walks on connected, non-bipartite graphs. For an oblivious adversary, the Markov set chain will converge to pi. The standard proof applies. However, if we look at a Markovian adversary, the Markov set chain may not converge to pi. As an example, consider these two weighted variants of the path graph with self-loops. So the values denote the weights of the edges. I wasn't able to draw self-loops very well, but there are self-loops with the corresponding weights at the ends. Now, all of these graphs have each node having weighted degree 3, so both of these graphs have the uniform distribution as their stationary distribution. However, we can define a Markovian adversary that chooses p odd if xt is odd, and p even if xt is even. You can verify that in this case, xt plus 1 equals xt plus 1 with probability 2/3. That is, it's biased to move to the right. So, of course, this walk won't converge to uniform. Nevertheless, we won't let this stop us from choosing as our adversary a non-Markovian adversary, so it's even more powerful, and we'll obtain the best results in this setting. We'll think of our adversary manipulating a given Markov chain P. And we'll have two types of adversaries, a standard adversary. Here, this adversary has to choose PT with entries that are between 1 minus epsilon and 1 plus epsilon times the entries of P. For a strong adversary, which is the same adversary as in the Azar et al. Paper, the adversary can choose any stochastic matrix B whose support is contained in the support of P, and then choose as PT the matrix 1 minus epsilon P plus epsilon B. For constant degree graphs, these are equivalent up to constants, so don't worry too much about the difference for now. Our main question will be, what's the largest value of epsilon such that the Markov set chain behaves like P? And we'll have four notions of what it means to behave like. These correspond to the stationary distribution, and then three times: the mixing time, the maximum hitting time, and the cover time. And again, our focus is on the undirected graphs of constant degree. So let me start by exploring hitting time, since these are the easiest to define. So here, this notation, expectation sub u, that means the expectation for a random walk starting at node u. HV will be the random variable denoting the first time we hit the node v. So little h sub uv is the expected time starting at u to hit v. And the maximum hit time, denoted t sub hit, is the maximum over pairs of nodes uv of the expected time to go from u to v. So now let me define robust variations of these hitting times. So we'll use a standard adversary. Otherwise, we'll need epsilon to be less than 1 over d if it's a d-regular graph. That's because if we ever reach a neighbor of some target node, the adversary can avoid hitting that node if it controls a 1 over d fraction of the probability. So we can define the robust hitting time from u to v as the maximum over epsilon adversaries of the expected time to go from u to v. And the maximum hit time, the robust version, is the maximum of the robust versions of the hitting times from u to v. So the hitting time robustness is defined as follows. We fix a large constant c, and it's the maximum epsilon such that the robust hitting time is at most a factor c larger than the standard hitting time. And we denote this by rho sub hit. Let's look at an example. The path and the cycle are the same up to constant factors. Let's think about the path. For the path, the hitting time is n squared, and as well, the cover time and mixing times are also a constant times n squared. An epsilon adversary can force the random walk to move right with probability 1 plus epsilon over 2. This says that the robust hitting time will increase by a factor of 1 plus epsilon divided by 1 minus epsilon to the n. So in this example, the hitting time robustness is, which again is the largest epsilon such that 1 plus epsilon over 1 minus epsilon to the n is a constant. So namely, it's a constant divided by n. Okay, now let's think about the hitting time robustness more generally. I just rewrote the definition again. An easy positive result is that the hitting time robustness is at least 1 over the hitting time. Again, positive results are lower bounds on the robustness. We can show a much stronger result, that the hitting time is actually at least 1 over the mixing time. The mixing time in general can be much smaller than the hitting time, although in this specific example of the path, these are the same. As an upper bound, or a negative result, the hitting time robustness is at most 1 over the average diameter. Here, the average diameter is you pick two nodes randomly and look at the distance between them. But for trees, we can show that the hitting time robustness is at least 1 over the diameter. So the diameter of a path is n, so this gives the value 1 over n for the path, which is tight. We can also show that for constant degree expanders, the hitting time robustness is a constant over log n. The negative result is new. The positive result follows from it being at least 1 over the mixing time. Let's turn to robust cover times. So let the random variable t denote the cover time, that is the time to visit all the nodes in the graph. Let t sub cov denote the maximum over starting nodes u of the expected cover time, starting from u. The robust version is the same, except now we take the maximum over epsilon adversaries. And the cover time robustness is defined analogously. We fix a large constant c. The cover time robustness is the largest epsilon such that the robust cover time is at most a factor c more than the standard cover time. And again, an easy positive result is that the cover time robustness is at least 1 over the cover time. I just rewrote the definition. But we can do better in many cases. So to explain that, recall this theorem by Matthews that improves earlier theorems by a constant factor, that the cover time is at most the hitting time times log n. The same proof applies to the robust cover time. That too is at most the robust hitting time times log n. As a corollary, if the cover time is at least the hitting time times log n, then the cover time robustness is at least the hitting time robustness. So this holds for most graphs. We conjecture that, in fact, the cover time robustness is at least the hitting time robustness for all graphs. And as a corollary, we obtain that for constant degree expanders, the cover time robustness is a constant over log n. Now let's turn to stationary robustness. Here we'll allow strong adversaries since the previous objection doesn't apply. But again, it's not crucial since we're thinking mostly about constant degree graphs. First, some notation. For a subset of nodes, let nt of s denote the number of visits to s up to time t. We can define the upper frequency of s, which is sort of analogous to an upper stationary distribution, in the robust setting by taking the maximum over strong epsilon adversaries of the lim sup of nt of s over t. And as a theorem, we can show that if epsilon isn't too large, then this upper frequency, pi plus of s, isn't too much larger than pi of s. Namely, it's order pi of s to the 0.99. And what is this value of epsilon? Well, t up is a variation of t mix. I won't go into it now. And d max is the maximum degree, of course, but we're thinking of that as a constant. As an application, think about an exponentially large graph. There are theorems of the form that certain bad configurations have negligible probability. Well, as a corollary, negligible events remain negligible even if we allow this amount of noise. Okay, now we turn to the robust mixing time. Again, these Markov set chains don't mix in a true sense, but we'll still define a variation of robust mixing time. First, let's define the ordinary mixing time. Let delta of t denote the maximum over starting nodes of the variation distance between xt and pi. The standard mixing time is the smallest t such that delta of t is at most a quarter. The robust version of delta t is when we take the maximum over strong epsilon adversaries. And the robust mixing time is the smallest t such that this delta plus of t is at most a quarter. The mixing time robustness is defined analogously. We fix a large constant c. It's the largest epsilon such that the robust mixing time is at most c times the standard mixing time. I just rewrote the definition. Again, it's easy to show that the mixing time robustness is at least 1 over the mixing time. Well, now we're using a strong adversary, so we actually get 1 over the maximum degree times the mixing time. And we have a theorem that the mixing time robustness is actually at least square root of this value. So this can be a significant improvement. For expander graphs, the mixing time is log n, so the easy bound gives us 1 over log n. This theorem gives us 1 over square root log n. But we can actually prove that for constant degree regular expanders, the mixing time robustness is a constant. I've stated several theorems. Let me just give you one proof idea. And that's for this theorem that the hitting time robustness is at least 1 over the mixing time. Here we establish a key lemma, namely that for any nodes u and v, the probability starting at u that we hit v in at most c times t mix steps is at least what you'd expect, namely the mixing time divided by the hitting time. As a corollary, something similar holds even with an adversary. So here, if we set epsilon equal to 1 over the mixing time, the probability that we hit v within c t mix steps is at least 1 minus epsilon to the c t mix times this t mix over t hit. So now we can divide the walk into epochs of length ct mix. The walk behaves the same pretty much whether we have a strong adversary, or whether it's just the standard walk. And this allows us to establish the result. And I think this key lemma can be useful elsewhere. In fact, we can use it to establish a simpler proof that expanders have hitting time order n, and hence cover time order n log n. Well, let me say a bit about previous work. At a high level, they take a different perspective. So first, let me discuss the work initiated by Azar, Broder, Carlin, Lineal, and Phillips. So our strong adversary is their adversary. However, they don't view it as an adversary, they view it as a benevolent controller. So their positive result would be that this controller can increase the stationary probability from p to the 1 minus epsilon, which would be a negative result for us. But the perspective is even more different when it comes to the times. So for example, they show that you can reduce the cover time for expanders to order n log n. So this doesn't really have an analog for us. Our adversaries are trying to increase the cover time, and they're trying to decrease it. There's been other previous work. So Chin, Moitra, Mossel, and Sandan looked at adversaries in Glauber dynamics. However, their work was particular to Glauber dynamics. There's been work about sensitivity of eigenvalues to perturbations, which can apply in some situations, but it doesn't give good bounds as far as we could tell. And finally, there was some work done with Doron, Moshkovitz, and O, showing strong results about lossless expanders, mostly about it kind of related to mixing, but we didn't study hitting or cover times. So to conclude, we introduced new notions of Markov chain robustness, and we proved new theorems about them. It's natural to ask whether we can obtain better bounds. So in particular, we have a few conjectures. I'll state 2 of them. One, we conjecture that the hitting time robustness is at least 1 over the diameter. We proved this for trees. Another is that the cover time robustness is at least the hitting time robustness. We proved this for most graphs. And finally, can we generalize and extend this theory? I'm hoping that this is the first paper in a line of work. All right, thank you.